Welcome to Excellent Grades Academy. This is Dr. Byson EM. In this video, we're dealing with tutorial sheet 3, which has an assignment on question 3 and question 4 from the University of Zambia School of Natural Sciences. All right, so we'll deal with some questions and then we're going to see how alkenes and how alcohols react. Okay, so let's get into this video without further ado. All right, so this is the mighty tutorial sheet 3. Question 1 says, provide the mechanism for each of the following reaction transformation. So now here, what they're telling us is that how do we transform this product here to this product here? Okay, so now if you look at the substrate, which is the organic compound that is reacting, this is an alkene. How do you know? Because there is a double bond here. And this alkene is reacting with an acid. This acid here is simply sodium, rather it's hydrogen bromide or bromic acid. And you know that an acid is a proton donor. Okay, an acid is a proton donor, and an alkene is electron rich. So this alkene that is electron rich is going to deprotonate this acid, meaning it's going to get a hydrogen from this acid. Let's show this mechanism. So how this is going to happen is that this hydrogen bromide here is going to be attacked by this alkene here. So when the alkene using the double bond attacks the acid, this bond here is going to break and the halogen is going to carry the electrons. So what this would result into is that there's going to be formation of a carbocation here, and the hydrogen is going to be added here. Now, if you look at an alkene, the double bond is formed by two carbons. There's a carbon here and there's a carbon here. Now, which carbon do you think the hydrogen is going to go to? The hydrogen is going to attach to the carbon that is less substituted. So between these two carbons, the hydrogen is going to attach to this hydrogen that is less substituted, and the carbocation is going to form on the carbon that is more substituted. That's why the carbocation forms here. Now, when this compound forms here, this carbocation that is here is adjacent to a ring. So what is going to happen is there's going to be ring expansion. So this methyl group that is here is going to shift to where the carbocation is, and there's going to be ring expansion. So initially there was a 3-membered ring. It is now going to expand to a 4-membered ring. Okay, and this where the ring is going to expand to, there were 2 methyls. So there's going to be 2 methyls here, and the carbocation which was here is going to move to here, which is here. All right, so now you form a carbocation that is inside of the ring, but you notice that the carbocation here is adjacent to this carbon here, and this carbon here is more substituted than the carbocation. So what will happen is that there's going to be an alkanide shift. This methyl is going to shift to where the carbocation is. So this is what we call a methanide shift. When the methanide shift happens, what you are going to have now is this. So this methyl shifts to there, and the carbocation shifts to here. Okay, and then the bromide that left in the initial steps is still in solution. So this bromide is still in solution, and it is negatively charged because it carried electrons with it when it was leaving. So this negative charge on the bromide is going to be attracted to the positive charge carbocation. When this happens, when this joins here, this reaction happens, then you're going to produce this compound there. Okay, so let me just draw it here. This is the product that is formed after the reaction is formed. So this is the reaction mechanism that takes place for this organic compound to be transformed into this organic compound. So that was part 1 of question 1a. Let's go to part 2 of question 1a. It says, what is the mechanism for this reaction here? So you know that this here is an alkene and it is electron rich. You know an alkene acts as a nucleophile. So first of all, it is going to attack this bromine. Okay, so this alkene will get one bromide, and then this bromine is going to leave. When that happens, the bromine is going to attach to the carbon that is less substituted. Okay, so it is going to attach to this carbon here. This carbon here, that's where the bromine will attach to. And the carbocation is going to form to this bromine, that this carbon here that is more substituted. When that happens, there is water in solution. This water that is in solution is going to act as a nucleophile. So this water will come and attack here on the carbocation, and the product of that reaction is going to be this one here. So there's a bromine here, and there's a water that has attached here. Okay, now you know that when oxygen has got 3 bonds attached to it, it becomes positively charged and it's unstable. This bromine that left is still in solution. So the bromine that is negatively charged will get this hydrogen here, and then this hydrogen is going to drop its electrons on the oxygen. So the final product that you're going to have is this product here, and the alcohol there. So this is how this compound is derived from that compound. So that's how this compound was derived from that compound. So always know that when you have an alkene, the alkene will act as a nucleophile and it will get one bromine from here, and then the reaction is going to proceed as we've explained in this reaction mechanism. So that was the 2 parts of part A of question 1. Okay. Question 2 was, provide a synthetic plan on how the following transformations can be carried out in good yields. More than one step is required. Show all steps clearly, including the intermediates. No reaction mechanism is required. Okay, so I'll just pick one of these, and I'll pick this complicated one here. All right. So now they're asking us, in more than one step, how do you produce this compound from this compound? Okay. So the first thing I'm going to do is that I'm going to react this alcohol, because I know this is an alcohol. It's here. I'm going to react it with an acid. Okay. An acid is a proton donor. So let me say I'm reacting it with sulfuric acid. This alcohol will act as a nucleophile and it will get the proton from the acid. So it's going to be protonated to be like this. When oxygen is bonded to 3 covalent bonds, it becomes positively charged. So when it becomes protonated, this one here is going to leave. When it leaves, it will form a carbocation intermediate here. This carbocation that is formed here is adjacent to this carbon here that has got a lot of methyl groups. All right, has got a lot of methyl groups. So there's going to be an alkanite shift, which is a methyl shift from here to here. So this methyl here is going to shift from here to here, which will form this product here. And this carbocation is going to shift to here, like that. Okay. So now, when that happens, The water that left will act now as a base. So this is the water that left here on this step, will act as a base, and it will get the hydrogen from here. So it will get this hydrogen, and then these electrons will collapse there, and it will form an alkene. So it will form an alkene. To form an alkene here. When this alkene is formed, I'm going to react this alkene in bromic acid, hydrobromic acid. And then I'm going to place this hydrobromic acid in peroxide. The reason why I'm pressing this hydrobromic acid in peroxide is because I want this bromine to join to the less substituted carbon between these two. If I didn't add the peroxide here, the bromine here would join to this carbon here. But since I've added the peroxide here, the reaction, the product that is going to form is going to be like this. So by virtue of me adding a peroxide to this reaction, what I've done is that this halogen is not going to add to a more substituted carbon here, but it will add to a less substituted carbon here. This is called the anti-Markovnikov reaction. Ideally, if there's no peroxide, if you react it just with hydrobromic acid, the bromine is going to bond to a more substituted carbon. But if you add peroxide there, there's going to be formation of radicals, and that is going to enable the halogen, which is the bromine in this case, to be added to the less substituted carbon. So this is how this, which is this here, product is formed from this substrate there, just by following these intermediates that I've drawn here and the few reaction mechanisms. So that was number 1B. Let's look at number 1C. So number 1C says complete the following reactions and give a detailed mechanisms of the following reactions. So here I'm going to pick 1 or 2. Okay, say I pick this one here. So first of all, what is going to happen is that this is an alkene. An alkene, when you're reacting it with an acid, there's always going to be deprotonation of an acid. You know, this acid is a proton donor, so it will readily donate this hydrogen here to an alkene, and that will form this intermediate here. Okay, so the hydrogen will form here, and then the carbocation will be here. Okay, and then what will happen is that this alcohol here, which is C2H5, the oxygen in this alcohol is a nucleophile, so it will come and attack here. Okay, so it will go and attack there, and it will produce this compound. So C2H5, and then there's a hydrogen that is attached. So the oxygen here is attached to 3 things. This one that left is negatively charged, so it will come and remove this oxygen here. Negatively charged, so we'll come and remove this oxygen, and this will collapse there, and then the final product will be this, which is an ether. So this is one product that is going to form. That is one product that is going to form there. So this is a reaction mechanism of how an alkene is going to act with sulfuric acid in an alcohol. Right, in an alcohol. Let's look at this. They're saying what is the reaction mechanism and how many products can form here. So first of all, this is an alkene. it is going to react with this bromine. So this alkene will get this bromine, this one will go, and it will form a carbocation intermediate here. This bromine will act here. What will happen is that either this bromine here that is in solution will come and attack here and will form this compound, or this same ion, cation here, may be attacked by this chloride that is in solution. So this chloride that is in solution can come and attach here and form this compound. Like that. So you can either have this compound here or this compound there. That's how it can be. All right, so that was question C. Let's look at question 2. Question 2 says, give the structures of the major products of the following reactions. Okay, so when you react an alkene with these conditions, what are you going to get? So let's start. So when you react an alkene in hydrobromic acid and peroxide, you're going to get this product here. So the bromine will be attached to a less substituted carbon of the two carbons that are forming the double bonds. And then when you react this product here, when you react an alkene with sulfuric acid in water, what you're going to have is an alcohol. Okay, so first of all, you're going to have protonation. You're going to have deprotonation of the acid, and the hydrogen is going to act here, is going to attach to a less substituted carbon of the two carbons that are forming the double bond. The ion is going to form here, and the water is going to attack there. So you're going to have an alcohol here. And then when you react an alkene in sodium permanganate, potassium permanganate at very low temperatures, you're going to have a diol, an alcohol. Okay, an alcohol, a diol. When you react an alkene in concentrated potassium permanganate at high temperatures, you're going to cleave the alkene. So there's going to be cleavage here. And then this part will be a ketone. And then this part here will be a carbon that is double bonded to an oxygen and another oxygen here. So this is what you're going to get. So those are the products, the structures of the major products that you're going to get once you react an alkene under these conditions. For the reaction mechanisms of these questions, we're going to make a video on it. You can click on the link below and see how they are formed. Okay. B. 2B says, consider the following reactions and deduce the starting material and draw the structure for each. So this is octene. This is octene. And then when you cleave it using potassium permanganate, it gives you these acids. So let's try to draw octene. This is 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. So when you react this in potassium permanganate under high temperature and you put an acid there, you cleave the double bond into hydrochloric acids. So now this hydrochloric acids has got carbon number 1, number 2, number 3. Okay, meaning that the double bond was on carbon number 3. Okay, so this is number 1, number 2, number 3, meaning that the double bond was here. Because if you cleave it here, then you're going to make this. And then the other one should have 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. So what happens is that if you put an alkene in permanganate at high temperatures, what you're going to make is you're going to cut the double bond into 2. And then this cut part of the double bond, you just add oxygen. Okay. So you just add oxygen. For example, I cut here. This is 1, 2, 3. The double bond was here where I cut. Where I cut, I put oxygen there. And the other hydrogen that remained here, I just put an OH. That's what happens. Okay. So that's what happens. Brings me back to okay, so that's what happens there. So this was the starting material for us to make these two. We started with this in order for us to make these two. Let's look at 2. Says this is nonene, and then we were making cyclohexanoic acid. So from here we were making okay, and we're making ethanoic acid. So we're making these two and then say what was the starting material. So I know that they just cleaved at this point here. Okay, so I know that where they cleaved was a position like this. So this is carbon number 1 outside the ring, carbon number 2. The other one has got 2 carbons, 1, 2. So I know if the double bond was here, so here they used ozone to cleave in dimethyl sulfide. If the double bond was here, then they cleaved here. Where they cleaved, they put an oxygen here. So you cut the double bond, the remaining part of the double bond here, you put an oxygen there. But then there are these OHs. So meaning there was an OH here, and there was also an OH here. So that when you cleaved here, when you cleaved the double bond here, what you remained with was a cyclic ring, and then there was a double bond that you cleaved, you added oxygen and an OH that remained, and the other one that you cleaved here. So this is where you cleaved. There was a double bond, you cleaved, you add an oxygen, and what remained was a methyl this side and an OH this side. So that is how they cleaved. Okay, so that is how they did the reaction. That were the starting materials in this question to find these products that they gave us. Okay, question 3. So question 3 is part of your assignment. Question 3 is part of your assignment. So this is an assignment, and only people who are registered on +260 975 497790 and are taking organic chemistry with Excellent Grades Academy will be able to see the video on question 3 and question 4. So video is already available. If you want to be part of the people who will be solving this question with me, you can register on WhatsApp on this number, and this video will be made available for you. All right. See you in the next video.